All right, so we are in multi-sim. So lab 3, there's really only one circuit for lab 3. There's not a bunch of circuits, but there's a lot of things you need to calculate and do in this lab. All right, I don't know how many pages it is, but I think it's like 15 or 20 pages. So you'll need to read through it thoroughly and make sure that you annotate everything that's required in the lab. And when it says, another thing that you guys need to understand is that whenever it asks you for a yes or no, usually it says, please explain your answer. Yes is not an explanation, okay? So I need to make sure that you understand this.
I just kind of think of a way to elaborate on it from you saw from the previous labs how I basically say.
So yeah, just keep up and just elaborate. Write whatever you know about it. And honestly, this helps me to know that you understand what's happening. So just take your time and make sure that you fill out all the answers. Okay, so, and I don't know if you guys have this or not, but anyway, the lab is already online, but I'm gonna go through this. So I'm gonna go ahead and build this from the image that you guys have on your lab, or the same thing I have on my lab. And the first thing we need to do is we're going to need a function generator. So I'm going to bring my function generator over here. If for some reason, can you guys see my far right-hand side with all my tools?
Yes, I can. Yeah, I can. I can see that.
All right, excellent. Okay, so the next thing we're going to need is a AC sine wave or a signal. So we'll go here and we're going to look at sources and power sources. And we have our AC sine wave. And we'll bring that out. Oh, nope, I don't want that one. You'll notice that this one right here has VRMS, okay? It's always best, I like just for the sake of it, I like using the one that has the volts peak on it. Okay, so I'm gonna change this one out and power sources, signal, here we go. AC.
Is there any way to change VRMS to V peak?
That's what I'm doing right now. What, did you watch me? Watch what I'm doing here. So instead of power sources, I clicked on signal voltage sources. AC, click OK, and look, volts peak.
Perfect, thank you. Yep,
you betcha. Now, I'm gonna go ahead and now I'm gonna get something called a multiplier, So probably the fastest way to do this is to go ahead and select all groups,
and just type in multiplier.
And just type in multiplier. And it should start to come up and look, there you go, multiplier. That's what it looks like. So we'll go ahead and put that out here. Now we have our multiplier. Then we need a summer, not a winner, a summer. So we're gonna come up here, same thing. We'll select all groups, all families, and we're gonna type in summer. Oh, it's called something else as well. Hold on a second. So we're gonna go under sources and control functions right here. And here we have it's called a voltage summer. So under control function blocks, we have something called voltage summer. We're gonna click OK, bring that out. And now we have our summer. Next thing we need is over here to the right. We need our spectrum analyzer. So we'll go down the list here. Here it is. There's our spectrum analyzer. And then finally, we need our oscilloscope, which you guys should be using the Tektronix oscilloscope. And that is, and of course, a ground. We need at least one ground. Okay, so there's all of our parts, our components that we need for our lab. So I'm gonna go ahead and wire this up the way it should be. So in this case, we have our X value, which are X inputs for our multiplier, which is right here, is gonna be connected to our AC. I'll explain that in just a second. We also have our negative side of the AC input hooked up to ground. Then we have our positive from our function generator hooked up to our Y input on our multiplier. And then we have our summer, which we hook up the output of the multiplier to our summer, meaning summing something, a product. And then we have our B connector on our summer going to the top part of our positive side of the AC supply. And then we have our output of the summer that's going to be going to the input of the spectrum analyzer and also to channel 1 of the oscilloscope. Also, I'm going to go ahead and duplicate, Control copy, Control V, so I can get me a ground for my oscilloscope. And nothing is hooked up to our T input here. And that should, oh, and our ground for our comment on the function generator. Okay, any questions? Any questions on how to hook this up so far? Of course, all this is in your lab. So, I mean, there's a perfect diagram in your lab of how to hook it all up. So I'm just wanting to know if you have any questions based on what we have here. Okay.
I'm good.
Okay. So I'm just gonna make sure something is correct in here. Basically, you're gonna be changing this, our function generator, to kHz, and it's gonna be 5 kHz. And then your voltage or amplitude, of course, in there in your lab is gonna be 1 volt peak. So now that we are set up for this, who can tell me what does this represent in our AM signal? Who can tell me what the frequency generator represents?
The envelope?
The what?
The envelope.
Nope.
Ah. Would it be the wave itself?
What do we call this? Yeah, it's a wave, yes, but what do we call it?
It's the signal you're receiving, right? It's
sine wave?
You were receiving it.
No, no. It is a sine wave. Right? But what are the 2 parts? What are the 2 parts of an AM signal?
Intelligence and carrier.
Okay.
Yeah, there we go. Yeah.
Mr. Anthony. So, Mr. Anthony, what part is this?
Wouldn't that be the carrier?
Nope. Good try. It's 50-50. I'm sure people can get it now. So what part is this?
That's the
intelligence.
All right, intelligence.
Intelligence.
Thank you, Dillson. So we have our intelligence. So that must mean this part is what?
The carrier.
Okay, Mr. Thomas. So our carrier in this case is not going to be 1 kHz. It's going to be 100 kHz. And then the 1 volt is fine for right here. Now we have our intelligence, we have our carrier, we have our multiplier, and then our summer between this and what's coming in here from our intelligence. And now we're going to have our output feeding into our spectrum analyzer and our oscilloscope. So we're going to start with, I know, we'll do the spectrum analyzer first. So spectrum analyzer, what do you think we should be reading on our spectrum analyzer? What are we looking for as far as the AM signal is concerned?
The amount of modulation.
Well, yeah. What else? What else do you think we should see on a spectrum analyzer? I know we haven't talked about this. I'm just seeing what you know. Now, you guys have seen, we have definitely covered this kind of stuff. We talked about it anyway, the signals, and through the PowerPoint as well, we talked about some signals that what we would have on the output. What kind of signal do you think we would have on the output? Remember, we're taking this intelligence and the carrier, we are multiplying those in order to get our value for the summer, and then we're taking our summer and we're placing it onto our, basically we could say our output, feeding into the transmitter or whatever, but it's coming into our spectrum analyzer. So what do you think we should have? Give me an idea what you think we should have on the output.
Square wave.
Nope.
More like a circular wave. Or
no.
Yeah.
Okay. Oh, here we go. Let me see. I'm going to draw on this.
I'm not really sure how to describe it, but it.
Okay. Do you guys remember something like this on the PowerPoint?
Oh yeah. Oh yeah.
What are those?
The 25 on each side, right?
There's the middle, which is the general, and then you got the high end and the low end.
Okay, so what would we consider this in? This right here.
The lower is the intelligence signal, or
okay, but what is that? Remember what side is that? I don't want to give it away, but we have that side and this side. When we think about the values, what's the value of this one?
The one that has it, the one that has one subtracted from it is
okay, and that's called what?
Difference.
All right.
Difference in sum.
There we go, Thomas. So we got the difference.
Sorry, I keep doubting myself because I don't think.
No, you're right, Thomas. We got the difference on this side and the sum on this side. So what do you think is on this side of this middle one?
That's like the main.
I'll give you a hint. What is that?
The carrier.
That's the carrier.
The carrier. The carrier, guys.
You're fine.
So in the center is our carrier, isn't it?
Yeah.
So in reality, what kind of value should we have here on the center?
100,000 kilohertz.
What kind of value should we have here on the difference?
5 kilohertz. All right, intelligent.
2.5, right? Because 25% of it.
Well, no, you're talking about power. You're talking about amplitude. We're talking about frequency right now. What kind of frequency should I have right here on the difference side? And there's a difference. So what does the difference come from? You guys nailed this.
The
Comes from the intelligence.
Okay, what is that? What would it be, Dennison?
1K hertz.
The function generator, I believe.
Wait, how much?
1K?
No.
Oh.
We have. Well, how much do we have here?
100K.
What did I set my function generator up to? For what frequency?
Is it 1K?
No. Do you guys remember what it was? Okay, I'm going to open it up. What do I have?
5K hertz frequency for
5K hertz, right? For my intelligence.
So one will be.
What's this one going to be then?
95,000 hertz.
Okay, and then what about this one?
105,000 hertz.
All right. Does anybody not see that? So now we're going to verify that. Let me go here for a second. this. Now let's see if what we just said over here is actually going to be true. So the first thing we need to do is we need to go ahead and make sure we set up our base, okay, for our information for the spectrum analyzer. So in this case, we're going to be looking at, for our center, 100. For our ends, going to be 150, 150K. For our start, we're going to start at 50K for right now. And then our span is going to be 100K. So that looks good, that looks good, that looks good. And then our resolution, we're going to set this at about 500 Hertz, just for now. And then our range, we're going to set that up to about 0.15. Oh, 0.15. Okay, so now we have those set up. We're going to go ahead and run it, and let's see what happens. And nothing happens. Let's see, what did I forget? That's good. 100 there. That's good. That's good. That's good. 50. 100 span. K, enter. Oh, my point didn't get put in there for the range. That's what happened. So let me try this again. 0.15. There we go. Okay, now, does this look familiar?
Yes, it does.
Wow, isn't that crazy? So what I'm going to do is I'm going to kind of open this up a little bit. And the way I'll do that is I'll stop the spectrum analyzer for a second, and I'm going to change this span to 50. And let's see what happens on that. That's a little bit better. Let me see if I can go to 25. Enter and start. There we go. That looks a little nicer. So now we have, what is this considered?
That's the carrier, right?
All right, Thomas. What is this one considered?
Intelligence, or the difference.
All right, and?
The sum.
All right, and the intelligence. So this information and this information, what's their relationship? Who can tell me? We talked about this before. What's the relationship between this one and this one? What kind of information is on this one?
Yeah.
You just said it.
The intelligence signal, the difference.
Okay. All right. So what kind of information is on?
It's a 5,000 hertz difference.
Okay. What kind of information is on this one?
5,000 hertz sum.
What type of information? What is
the intelligence?
Intelligence. That's all we're worried about right now. Is this what's the difference between this intelligence and this intelligence?
One's high, one's low.
Nope. I mean the information itself. What's the difference in the information of those two?
I mean, like the number, like the 10, like
no, not a value. The information itself. In other words, intelligence is something like an announcer, you know, or a radio broadcaster. What's the difference between those two? So if this guy over here, I'm going to stop this simulation for a second. If this guy over here is Mr. Intelligence, let's say he's a broadcaster and he's talking about the baseball game that's happening, okay? You know, you got two on base and so forth. that information, that whatever he's saying here, how does that relate to this and this?
That is the information to the intelligence.
You got information here and you have information here.
We know it's the same type of information.
Oh, thank you, Thomas. That's what we're looking for. These are exactly the same type of information. That's important because we're going to look at something else.
I mean, we
later.
kind of discussed that already. Sorry, I thought I had to kind of elaborate a bit more on it.
No, that's it. So this is the same information as this. Now, this is going to be important, especially when we start getting into demodulation. Because if you remember what we said when we get into demodulation, we don't care about two of these. We only need one of them, right? So in the end, we're going to be using a detector or diode, and it's going to remove either this half, this bottom part, or this upper part, because we only need one. But for the sake of this combining or this summer right here, we have the difference of the center and the sum of the center. Everybody with me?
Yes.
Now, the next thing we want to do is, here's where we need to make sure we know how to do the measurements. This is probably one of the most important parts. And when you do your graphs in your lab, drawing some wiggly lines on your graph does not denote you understand what's happening, okay? You need to make sure that you know how to do the measurements, because those measurements are important to make sure that whatever your intelligence is over here and your carrier is over here, you know what to expect over here. Make sense? So you see this little slide bar up here, this vertical slide bar? Everybody see that?
Yep.
Okay. So I'm going to move that just kind of close to the peak right here. Instead of me trying to go to the peak and guesstimate it, here's what you're going to do. You're going to get a little bit close to the peak. I got a little bit of a gap here between the vertical line and the peak. I'm going to put my cursor on the triangle here, and then I'm going to right click on it. You see where it says go to next Y max? I'm going to click on that. And look at that. It takes me right to the very, very peak of that signal. Then I'm going to come down here and say, oh, what is my reading in frequency? Would you look at that? What do we have?
We have 95,000 hertz.
Well, we're going to put it more exact as you see it on there. You're not going to write just 95. What do you see?
94.922 thousand hertz.
Okay, and what part of this is the signal? Is this the sum or the difference?
This is the difference signal.
Okay, so there's our value for the difference. Now, that's just the frequency side of it. Now we can look over here to the right and see what the amplitude is in voltage. You guys see that?
Yeah.
We got 505.271 millivolts for the peak of this value right here for the difference of the signal. So that's how we measured that part. So now I want to come over here and let's just verify that this is supposed to be what? What value should we have here for our frequency?
100,000.
Okay, so I'm going to move this over a little bit, get a little bit close to it, and then I'm going to do it, right click on it again, go to next Y max, and I look at my value and look at that. That is really, really close for our 100 kHz. In this case, because of the tolerance and the values and stuff within our summer and our multiplier, it's actually going to come out to be 100.195 K. These are the types of values that you need to be putting down in your labs. And then we have over here, we know that this amplitude here is much greater than this one, and we see we have a voltage of 838.382 millivolts. So let's go to the last one. Get over a little bit close to it. Go to next max, and look at here. We are almost at 105, but not quite. So we want to make sure that we annotate our frequency at the sum of the carrier, plus our voltage, which here in this case is 487.024 millivolts. All these values are just a slightly different, but they're close, but that's the kind of values that you should be annotating on your labs. Just to say that this is 100, this is 95, this is 105, does not tell me that you understand thoroughly what's happening here. Because that's just a mathematical equation, that's all. We want to see values of our actual measurements in our lab.
Yeah, I rounded up on a lot of them on that second lab, so I do know what you're talking about. From now on, don't round up. You still want us to keep it at what, 2 decimal places? Where do you?
Yeah,
how many decimal?
2 decimal places is fine. It shows me that you actually understand it and see it.
Gotcha.
Okay. Does anybody have any questions on the spectrum analyzer?
No, I think I got it.
Okay, so I'm going to move this over a little. I'm going to shrink this down a little bit. Keep it up there. And then I'm going to bring up my oscilloscope. Now, before I turn on the oscilloscope, can anybody tell me what kind of waveform we should be able to see here? Because we have physically combined our carrier and our intelligence together. And we should be creating something special on our oscilloscope. Does anybody know what that special oscilloscope signal might look like?
Aren't we looking for like an AM waveform? Like where the two are combined?
Absolutely, very good, Tess, very good. So what else would it look like? So you're on the right track, Tess. What else would the signal look like?
Would it be the envelope?
Oh, yeah. All right, Mr. Anthony, you're hired. So it should look like an envelope signal, which are those things that we kind of drew out, you know, before or whatever we looked at on the PowerPoint and so forth. So let's turn this on and let's run this for a second and see what happens. I'm going to go ahead and hit auto set, which we should always do whenever we start the oscilloscope. And there we go. So right now our time-based division, that's a little bit too short. We're going to go ahead and open up. And also, just in case you don't know, don't try to, you see where the finger is here on the times per division, the second per division here? Just let your mouse, don't press on any button on your mouse, just leave it there and then use the arrow keys on your keyboard to make adjustments. Oh, would you look at that? So I'm going to go over here to my amplitude, leave my mouse there, and use my arrow keys to kind of raise up that signal where I got a full signal. We go back a little bit to my seconds per division, and whoa, whoa, whoa. So you're thinking, well, shoot, man, I can't hardly see that. So if you want to stop that and do it just a single sequence, come over here to the right, and there's something called single sequence. Click on that, and it'll give you one sequence on the screen. That way, you can actually look at the waveform and determine, here we have a peak-to-peak value of 3.99 volts. 3.99 volts. So who can tell me a little bit about this signal now that we've talked about it before in previous classes?
It looks overmodulated.
Oh, very nice, Thomas. It looks a little overmodulated. I agree. It does look a little bit overmodulated. What else do you know about this signal?
Usually there's an envelope to accompany it. We got to figure that out.
Okay, so let's see who's really thinking. Okay, who can tell me the relationship between this signal here and this over here on the spectrum analyzer? Who can tell me some kind of relationship between those two?
Oh shoot, what is this? And the peak voltage should be the same. The peak voltage on the oscilloscope should be double the peak voltage.
Okay, I'm trying to remember. I'm trying to see what you're talking about here. So you're saying the peak to peak or like peak?
Give me a second. I might be very wrong.
No, that's okay. You're on the. You're thinking on the right track. That's for sure. Oh, missed it. So I'm just trying to set this up so we can see the voltage here. All right, there's our peak value for the center frequency, which is 816 millivolts. We have a peak to peak here. Hold on, let me do this math real quick, and let's just see where that stands. And 3.99, 2, and then we have 816.181, second EE, -3. And we'll take this side over here and look at that again. 471 plus 471.292, second EE, -3. Plus, what's the other one? We have 48.979, -3. And that is, messed up, hold on. Oh, yeah, there we go. Okay, so that is pretty close for our peak and peak here and our peak here. So in other words, what Tess is saying is that, I think this is what she's saying, the sum of this one peak, and this one peak, that's going to come out to be about 1.74 volts. Okay, about 1.74 volts. So I see over here on our oscilloscope, we have 3.99 volts peak to peak. So what this is over here is just our peak. So what are we actually looking at here for peak?
2.
We're looking at the smaller, the smaller ones.
Wait, no, what?
Double the peak. It's like you're looking at double because you're looking at peak to peak, right?
What this is peak to peak right now from this point
Right.
here.
So that's double what the other one was.
Volts.
You said it was 1.74, right?
Right. The 1.74. So in other words, what is the peak here? This is peak to peak. How much value do we have for peak? From this center line up or center line down, doesn't really matter.
We have.
Don't round it up.
We have
Come on, guys.
1.99.
Okay, 1.99. Very good, Denelson. We have 1.99 for half of this, correct? So that 1.99 is pretty close to the sum of these, isn't it? 1.99 compared to 1.74 on this side. So it's pretty close. It's pretty close. Now, the other question is that over here, since we're looking at peak to peak, which part of this signal right here is intelligence? I'm going to go ahead and change them. Oh, shoot, we got to run it. Oh, never mind. Hold on.
Are you asking like the rising and falling edge?
No. Oh, give me ones. Here we go. Let me get this set back up again real quick. Hold on. Okay, so I'm going to change this to. So here's our frequency. Do you see what's happening here? This is our carrier frequency, which is coming in on this signal right here, which is 100 kHz. We have combined our intelligence and our carrier together to create this envelope. Now, this is an envelope, meaning that where is my intelligence on this signal? Where is my intelligence on this signal? We talked about this before in a class. Where's the intelligence part of this signal?
The intelligence would be talked about this before.
We did kind of a demonstration on the PowerPoint. It kind of showed you what happens when you combine the two signals.
I think the intelligence would be either be the envelope around on it, or it'd be
okay.
or it'd be.
All right, Thomas. What part, guys? What part is the envelope?
That the envelope would be.
Okay, let me do this. I'm going to go ahead and put a drawing. I'm going to put
it kind of be the wavelength on the top and bottom of the wave on the oscilloscope.
What do you mean, like right here?
Yeah.
So you're saying this part, or this part?
The first one is that
okay at the top. So all right, so Thomas, so tell me if this is right. So our intelligence, what does our intelligence wave look like? Anybody? The intelligence wave, what does it look like? The guy speaking over here on this function generator.
It's
what kind of waveform?
It'd be the sine wave.
Sine wave. So it's going to look something like this, right?
Correct.
Is that correct?
Yep.
And then the carrier part, which is this part, right? 100 kHz. The carrier, if you remember, is going to look like this.
Yeah, it'd be more jaggedy.
Right, more jagged. Very good, Thomas. So it's going to look a little bit like this. So I know it's not perfect. So if I combine these two, what do I get? If I combine that intelligence and that carrier, what do I get?
What's on the oscilloscope?
Nicely done, Thomas. Very good. So here is my waveform for the intelligence, right? And then all this in between is my carrier right there. So what I want to know is this top part right here the same as this bottom part right here?
Yes, because you haven't taken half of it away, right?
Very good, Matt. So
now, but where you trace it, how is that not the same as the leading and falling edge of the wave? That's what I was trying to say, like up the, the leading and falling edge of the actual waveform.
Wait, you lost me, man. Leading, which part are you talking about?
Yeah, like the leading part of the wave would be, whatever side you're going towards, and the falling. So like in this case, the leading would be on the right and the falling would be on the left. So as you go up the wave, that would be your falling, leaving, falling. So basically it would, same thing as that blue line you just drew, not in the middle, but up, tracing the line. Yeah.
Yeah. So this wavy line right here represents this, correct? The intelligence?
Right.
So whatever the amplitude is of the intelligence, that's what dictates the shape of the carrier.
Okay.
So let me see if I can erase just this part here. There we go. Oh, come on. Hold on, lost it. There we go. Okay, so here we have our intelligence here. Intelligence here riding on the carrier. and we also have the bottom part again. So remember, this is called an envelope, right? So in reality, what was the information, what was the relationship between this information and this information here?
That both the intelligence signal.
Right, they're both exactly the same, right, Thomas?
Correct.
So here we have the oscilloscope version of all this. Which part of this, what's the relationship between this waveform here and this waveform down here?
They're the same signal.
Same signal. So basically what's going to happen is that whenever we get this to the demodulator, we are going to slice this envelope right in half, and we're going to get rid of all this stuff on the bottom or all that stuff on the top, and we're going to end up with just this part of the waveform, because we don't need two of the same intelligence coming through. We only need one because they are both exactly the same. That's why when we build our, you guys are going to be designing this, and I don't know if it's going to be a bonus or what yet, but you're going to have your, I'm going to give you your own parameters, and you're going to have to create and design an AM modulation, demodulation circuit based on the parameters that I give you. And you're going to have to be able to show me that you either got rid of the lower side or the upper side. And you're also going to show me how that relates to the signal on the oscilloscope itself, and how you got rid of half of this. That's all coming up. So it's not, I mean, we still got a little ways to go, but it's coming up. You guys will be designing this. I need to make sure that you understand what's happening in this signal on the oscilloscope and also on the spectrum analyzer. That's the most important part. Does that make sense?
Yep. Now, is it better to pick one or the other, like the higher end or lower end of the envelope?
It just really depends on the frequency itself, the transmission of it. Because remember, the higher frequencies will come through a little bit better than the lower frequencies, but it really, overall, it doesn't matter. A lot of times there's design based on what components they have to be able to bring this in on their demodulation side. But that's where it's kind of left up to you. It doesn't really matter to me whenever you do it, as long as all the signals and waveforms are correct for your final output. All right. Are there any other questions? This is basically what we're going to be looking for in our lab for lab 3. This is the kind of stuff you're going to be looking for. So you're going to be looking at the spectrum analyzer and the oscilloscope, the multiplier, the summer, the carrier frequency, and the intelligence frequency. It's kind of things we talked about already, but now you actually get to put it all together and do all the measurements.